Ambilani.
Current electricity. Okay, our new topic is current electricity. We have studied the basics in this chapter, current electricity, in our 8th class. Okay, your 8th class, we have studied the basics in current electricity. Okay, you know that what is meant by a charge? When does the flow of charge takes place, and what are the requirements for making a simple circuit? Okay, and how does a bulb glow when it is connected to a cell or battery by connecting wires, and so on. Okay, in this chapter, in this class, we will study the advanced topics in current electricity. Okay, first introduction. Introduction. And current electricity means flow of current means flow. Electricity means electrons. Electrons flow is called current electricity. So, in your previous class, you have studied that when a bulb is connected to a battery through conducting wires, okay, then the bulb glows. Okay, it gives light energy in all directions when it is connected to the cell. This is cell. These are connecting wires. Okay. So an electric circuit consists of some active elements. Electric electric circuit consists of some active elements. Some active elements means the elements which supply energy, electrical energy. Okay, for example, a battery or a cell. Active element means the element which supplies energy. Battery or cell. Next, passive elements. Passive elements means the elements utilizes energy, utilizes the electrical energy which is sent by cell or battery. These passive elements are basic passive elements are anything which utilizes the energy which is sent by active elements. This figure, bulb. Bulb utilizes this electrical energy supplied by the cell and glows. Okay, gives light energy, heat energy. Okay, that is passive elements. Passive elements. Okay, and this bulb contains a filament inside it. When the current is passing through that filament, it becomes bright. Okay, when the current is passing through the filament, which is heating element. Okay, that filament converts this electrical energy into heat energy. As a result, this bulb gives electrical light energy to us. So that is called passive element. Okay, so electrical circuit consists of two types of elements: active element and passive element. And next important one is this conducting wire. This conducting wire is made up of a conductor. This conducting wire is made up of a conductor. Okay, conductor means metal. Okay, metal. These conducting wires are made up of a metal which is enclosed by the insulating material like plastic material or rubber material, insulating material. Okay. When the ends of the bulb are connected to the terminals of the cell. Cell has two terminals. One is called positive terminal. Another one is called negative terminal. Two terminals are there. Okay, there is some potential difference exists between these terminals. When the ends of the bulb are connected to the terminals of the cell, then the electric current starts to flow through the conducting wire. Okay, and reaches the bulb. Okay, the bulb utilizes the current and glows. So first concept in this chapter is electric current. Electric current. Electric current. Okay, current means flow, electric means electrons flow. Okay, at a room temperature, the free electrons in a conductor move randomly with speeds to the order of 10⁵ meters per second. The free electrons. The conductor moves randomly at 10⁵ meters per second. So, free electrons in a conductor, that is nothing but a metal, okay, moves randomly at 10⁵ meters per second at a room temperature. Suppose this is an electron moves some distance in this direction and like this. This is motion is called random motion. So at the room temperature, the electrons moves randomly with the speeds in the order of 10⁵ meters per second. And since the motion of electrons is random, there is no net charge. There is no net charge flowing through any imaginary plane, in a conductor. Suppose this is a conducting wire. This is a conducting wire. Okay. This is suppose an imaginary cross section. This is an electron which is very close to that imaginary cross section. So initially it moves in this direction, next like this. Okay, so this electron does not cross this imaginary cross section in the conductor. Okay, similarly, the electrons on either side of the imaginary cross section moves randomly with the speeds 10⁵ meters per second. Therefore, there is no net charge flowing through this cross section. Since the motion of electron is random motion, no net charge is flowing through the imaginary plane passing through the conductor. Since the motion of electron is random motion, no net charge is flowing through an imaginary plane. In a conductor. So there is no net charge flowing through this cross section in this conductor at the room temperature. Okay, here please observe that these are the ends of the conductor. These ends are not connected to the cell. This is just at the room temperature. This conductor is at room temperature and it is not connected to the terminals of the battery. So when the conductor is at room temperature, the electrons are in random motion in the conductor and no net charge is flowing through any imaginary plane in the conductor. Therefore, no net charge is said to be flowing through that cross section of the conductor. That means number of electrons traveling from left to right is equal to number of electrons traveling from right to left. Therefore, number of electrons crossing from left to right is equal to number of electrons crossing from right to left. For example, 5 electrons are able to cross this imaginary plane in the conductor from left to right, and at the same time, the same number of electrons are also crossing the same imaginary plane from right to left. So there is no net charge flowing through this imaginary plane in this conductor when the conductor is at its room temperature. When the conductor is at its room temperature. But when the ends of this conductor but when the ends of this conductor are connected to terminals of a battery. Here, the ends of the conductor are connected to terminals of a battery by a conducting wire. There is some potential difference created across the ends of the conductor. Okay, there is some potential difference created across the ends of the conductor because this cell, the potential difference across the terminals of the cell is say B. B is the potential difference between the terminals of the cell. Then this N is here, this N is connected to positive terminal. Therefore, this end of the conductor is at positive potential and this end of the conductor is at a negative potential. Therefore, there is some potential difference across the ends of the conductor, which is equal to potential difference across the terminals of the battery. So when a constant potential difference is applied between the ends of the conductor, as shown in the figure, an electric field is produced inside the conductor. Electric field is produced inside the conductor. Electric field is produced when potential difference is applied. This electric field exerts force on the electrons. This electric field exerts force on the electron. Suppose, for example, this is an electron. Okay, this is a regular charge electron, free electron, and the electric field is existing in the conductor from left to right, whereas the electric force exerts on the electron from right to left. Okay, you know that in an electric field, positive charge experiences force in the direction of electric field, and negative charge experiences the force in the direction opposite to the direction of field. Okay, so here the electron is negative charge; it experiences electric force, which is opposite to the electric field, and this electric force is equal to minus E into E bar. Okay. E is small e is charge of the electron and capital E1 is electric field. Okay, minus sign indicates that this force and electric field are opposite to each other. So every electron within the conductor, every free electron within the conductor subjected to a force minus E, small e, capital E bar, and move overall in the direction of increasing potential. In the direction of increasing potential. In the direction of increasing potential means opposite to electric field. In the direction of electric field, potential decreases. Opposite to the direction of electric field, potential increases. Therefore, we can say that this conduction electron subjected to a force minus E, small e, E bar, and start to move in the opposite direction of the electric field, that is in the increasing potential, in the direction of increasing potential. And during their motion, the conduction electron undergoes multiple collisions with the other free electrons as well as the remaining structure of the conductor. And when this conduction electron collides with the lattice of the conductor, it loses its kinetic energy and sometimes it comes to rest momentarily. So after it comes to rest momentarily, again it experiences the electric force opposite to the electric field direction and starts moving again until it undergoes next collision. Okay, in that way, these conduction electrons moves opposite to the electric field in the direction of increasing potential. So during their motion, they undergo collision with the lattice structure and with the other free electrons. Due to the continuous collisions, okay, that kinetic energy of these conduction electrons are transferred to the lattice structure of the conductor. Okay, lattice structure of the conductor and increases the vibrational energy or thermal energy of the atoms. Okay, as a result, due to the continuous collisions with the atoms of the lattice structure and with the other electrons, okay, these electrons move slowly along the conductor, and we can say that it acquires a velocity called drift velocity in the direction opposite to E bar. And this drift velocity is in the order of 10 power minus 4 meters per second, or 10 power 9 times smaller than the average speed of the electrons between the collisions. Okay, so when the conductor is connected to the terminals of a battery, potential difference is applied across the ends of the conductor. As a result, the electric field is developed within the conductor, and due to this electric field, each conduction electron experiences an electric force which is in the direction opposite to the electric field, or in the direction of increasing potential, and during their motion, they undergo collisions with the lattice structure of the conductor, and finally it moves very slowly at the speed of 10 power minus 4 meters per second in the direction opposite to the electric field. The speed gained by the electron due to the potential difference is called drift velocity, and the drift velocity is in the order of 10 power minus 4 meters per second. So when the potential difference is applied, across the ends of the conductor, the conduction electrons gains a velocity called drift velocity, which is in the order of 10 power 4 minus 4 meters per second. 10 power minus 4 meters per second. So with this velocity, it moves along the conductor in the direction opposite to the electric field. So drift velocity is denoted by Vd. Drift velocity is denoted by Vd, which is opposite to E bar, which is opposite to E bar. This is the difference of motion of electrons when the conductor is at room temperature, and when the conductor is connected to the terminals of a cell. Now, the definition of electric current. So, due to the movement, M-O-V-E-M-E-N-T, due to the movement of charge through an imaginary cross section in a conductor, okay, net charge is said to be flowing through that cross section, and that is nothing but current. So, current is defined as the rate at which net charge passes through a cross section of the conductor. The rate at which net charge passes through a cross section of conductor. The rate at which net charge passes through a cross section of conductor. Okay, so it is denoted by I. Current is denoted by I. This is rate of flow of charge. That is dq by dt. I is equal to dq by dt. Rate of flow of charge. So this dq by dt is the current rate of flow of charge. This dq by dt. This current is called instantaneous current. Instantaneous current. That means the rate at which charge flow takes place at a point of time. Okay, at a point of time. I instantaneous is equal to dq by dt. This is instantaneous current. Next, for the given time interval, the current is called average current is equal to I average, that is equal to delta q by delta t. This dt is infinitesimal time interval, whereas this is finite time interval. So for the finite time interval, the charge flow is said to be average current, whereas for infinitesimal duration of time, okay, the charge flow is called instantaneous current. Instantaneous current means current at any point of time. Average current means the net charge flowing through a cross section in a finite interval of time. Finite interval of time. Next units. In SI system, unit of current is equal to charge divided by time of formula. So for charge coulomb per second, this is called ampere. So unit of current is ampere. In SI system, it is one of the fundamental unit in SI system. Unit of current is ampere. So 1 ampere is equal to 1 coulomb per second. An ampere is equal to 1 coulomb per second. Okay, this is about current. We will discuss the extra points in current in the next class, and we will do some problems on current also in the next class. Okay. Okay, Nana. Thank you very much for attending the class. From tomorrow onwards, we will do, from tomorrow onwards, we will discuss more concepts in this chapter. Also, we will do problems on current. Okay, there are some extra points in current. There are some special cases in calculation on current. We will discuss them in the next class. Bye.